USB-C. The Universal Standard, a comprehensive analysis of USB Type-C. The introduction of the USB Type-C connector, commonly referred to as USB-C, marked the most significant shift in peripheral connectivity since the original launch of the Universal Serial Bus in the mid-1990s. For decades, the industry struggled with a fragmented ecosystem of connectors: Type A for computers, Type B for printers, and a confusing array of mini and micro connectors for mobile devices. USB-C was engineered to end this fragmentation by providing a single, small, and extremely powerful interface capable of replacing almost every other cable in a technician's kit. It is not merely a new shape for a plug. It is a fundamental rethinking of how power, data, and video signals are negotiated between devices. Physical engineering and the reversible design. The most immediate feature of the USB-C connector is its physical symmetry. Unlike every previous version of USB, which required the user to orient the plug correctly before insertion, USB-C is reversible. This was achieved through a highly sophisticated 24-pin design. Inside the connector, the pins are arranged in two mirrored rows of 12. When you flip the cable over, the internal logic of the port automatically detects the orientation and reassigns the signals accordingly. This 24-pin layout is what gives USB-C its incredible versatility. It includes dedicated pins for high-speed data transmission, legacy USB 2.0 support, power delivery, and sideband signals for specialized functions. Because the pins are so densely packed, the connector is surprisingly robust despite its small size. It is designed to handle at least 10,000 insertion and removal cycles, making it durable enough for years of daily use on smartphones and professional laptops alike. Data transmission, from superspeed to USB 4. A common point of confusion is the distinction between the USB-C connector and the USB data protocol. It is vital to remember that USB-C is just the physical shape, while the data protocol determines how fast information moves. A USB-C cable could be carrying slow USB 2.0 signals, or it could be carrying the cutting-edge USB 4 protocol. USB-C was designed to scale with the industry's needs. Under the USB 3.2 specification, USB-C can utilize two sets of high-speed data lanes simultaneously. This is referred to as multi-lane operation. By using both lanes, the interface can reach speeds of 20 gigabits per second. With the arrival of USB 4, the architecture moved toward a packet-based system similar to Thunderbolt. USB 4 can reach speeds of 40 gigabits per second and even 80 gigabits per second in its latest iterations. This massive bandwidth allows a single USB-C cable to handle the data requirements of high-performance NVMe external drives and high-resolution video streams at the same time. Power delivery and alternate modes. Before USB-C, almost every laptop manufacturer used a unique, proprietary barrel connector for power. USB-C solved this through a technology called USB Power Delivery, or USB-PD. Unlike standard USB charging, USB-PD allows for a sophisticated negotiation over a dedicated configuration channel pin. The device tells the charger exactly how much voltage and amperage it can safely handle, with the latest specifications supporting up to 240 watts. Furthermore, USB-C features alternate mode, alt mode, which allows the 24 pins to be reconfigured to carry different types of signals. The most common is DisplayPort alt mode, allowing a computer to send a native video signal directly through the USB-C port. This is why many modern monitors can connect to a laptop with a single USB-C cable that provides video, connects the monitor's built-in USB hub, and charges the laptop simultaneously. Other alt modes include HDMI and Thunderbolt, which allows the PCI Express bus of the computer to talk directly to external devices like high-speed docking stations. Cable identification and the eMarker chip. Because all USB-C cables look identical on the outside, it is impossible to know their capabilities just by looking at them. A cable that came with a smartphone might be designed only for charging and slow USB 2.0 data. To solve this, the industry uses logos on the cable, over mold, to indicate maximum data speed and power capacity. High-performance USB-C cables also contain a small integrated circuit called an eMarker chip. This chip acts as the cable's identity card. When you plug the cable in, the computer reads the chip to find out if the cable is safe to handle 100 watts of power, or if it is capable of 40 gigabit speeds. If the eMarker chip is missing or reports low ratings, the computer will automatically limit performance to prevent the cable from overheating or catching fire.